Guillaume est directeur de la recherche et développement chez CIDCO. Il a étudié les mathématiques à l'Université de Montréal et le génie logiciel à l'Université du Québec à Montréal. Et puis ses intérêts sont dans la recherche, sont dans l'intelligence artificielle, le machine learning, les systèmes intégrés et la cybersécurité. Le titre de sa présentation est Comparative Analysis of Machine Learning Algorithms for Benthic Habitat Classification. Guillaume?
Merci. Yes, so, well, thank you for being here. This is basically one of two presentations that we're going to be doing at CIDCO on benthic habitat classification. The other one will be done by my colleague Ali, which will touch in the more GIS-oriented matters. From my end, we're basically going to be touching the surface from an algorithmic point of view. Just to add a little bit of context, why does benthic habitat matter? Basically, the ocean economy is estimated to be reaching $3 trillion by 2030. And this includes industries like fisheries, oil and gas, commercial navigation. And the bottom line is that this entire economy rests on accurate knowledge of the seafloor. Sadly, over 90% of the ocean floor hasn't been properly mapped. So we have a problem here. So this is why benthic habitat mapping matters, basically for three reasons. First of all, we need better knowledge of the complex interactions of ocean processes, but we also need to have data in order to foster favorable stewardship and better management and policies of ocean resources through data-driven decision-making. Finally, all this combined yields a better profitability for all the industries through sustainable economic growth, because if we basically take everything away from the resource, there's nothing more to be gained from it. So obviously, one of the big problems about benthic habitat mapping is that getting there is fairly hard. Covering ground is costly, and identifying areas of interest requires specialists to develop habitat models and such. So the solution has been pretty much within our reach for the past years. We can cover large surfaces using remote sensing, either through multi-beam echosounder systems, airborne LiDAR, or satellite imaging. We can limit ground truthing to few spot checks, and from there we can use AI and machine learning to fill in the gaps. And this is what we're going to be demonstrating here. Of course, you can meet the team. Which we have at CIDCO, we have our own hydrographic vessel. We have a team of fearless hydrographers, which will stop at nothing to get that ground truthing data. We have the proper computer hardware for it, and we have the algorithms for classification. So the technique in itself is fairly simple. It's been fairly documented. Vincent Lecourt, which is within the crowd at the moment, so hi Vincent, has fairly well documented the field of marine geomorphometry. Basically, we take bathymetric products, and from there we derive terrain attributes, which are basically numerical proxy variables and other environmental variables, and we basically use this combined with ground truthing data to derive an habitat map through an habitat model. To this end, CIDCO has undergone several MBES campaigns, notably on Quebec's North Shore. I'm going to be talking about three of them today: Golbou, Franklin, and Pointe-aux-Anglais. The data is basically your standard multi-beam echosounder system data. It's processed down to a 1 meter DTM using Cube and with minimal aberrations. As far as ground truthing goes, we've had access to DFO's database, which includes about 1,000 ground truthing stations, and this database is increasing every year. So hopefully we get more and more data on the St. Lawrence River, especially on the north and south shores, so that we can feed more data to this model year over year. So the process is relatively simple. We take the seafloor geometry data, which in our case is multi-beam echosounder system. But since we're using a 1 meter DTM, it can also be used for LiDAR data, which is one of the main purposes of the project. So basically, we take this data and we use supervised learning to classify the different habitats that are contained into DFO's database. So to that end, we basically enrich the ground truthing data using a neighborhood radius search to build the training data for the AI to basically learn from the different proxy variables available to it and give us our classification. As far as feature engineering goes, we used a classic set of features which are derived from basically 3 big characteristics. First of all, we have a set of variables here, the sum, omnivariance, eigenentropy. The first category are all issued from the local covariance matrix. So basically they are related to the different rugosity and geomorphometric characteristics around the neighborhood of the point. We have moment-based proxies, which are the first order and second order. So basically everything related to slope and edge detection is contained into that second set. And we have different height parameters. You'll see in a second, since we're operating in a 2.5D conical view, these proxy variables kind of give us a little bit more info on the actual objects that we're scanning. So we've obtained fairly good results. We've landmarked several algorithms for the sake of not having to delve into the details of each and every one of them. We've retained 4 big ones. K-nearest neighbors is a classic. Basically, we're looking for ideas for points that are similar, and the most similar points will have will give us our class. One of the big dangers from this algorithm is obviously overfitting, since we're calculating proxies over a neighborhood. Kind of makes it obvious that a certain point will be self-similar to its neighborhood, therefore the bias. So we have to take this one with a little bit of with a grain of salt. Gradient boosting, gradient tree boosting, which is kind of like the successor of the classical random forest algorithm, which is kind of omnipresent in the most, let's say, layman and machine learning toolkits. We can achieve 90% accuracy on classification on the ground truthing data that's been provided by DFO. For sake of curiosity, of course, the support vector machines is a very popular algorithm. Our colleague from Axis just mentioned that this was one of the algorithms that they were using in their SDB process. And just basically as a landmark feature, the naive Bayes algorithm, basically if we just consider each and every proxy variable as independent, just how good a classification can we get? And we get a fairly poor figure. So this tells us that there's a huge information gain in between pairs of factors, probably a lot of correlations. This is mostly for personal consideration. The results are basically habitat maps. We use the standard categorization, that are given by DFO, which are not ideal. We'll talk about this a little bit later, but basically it goes from bedrock through blocks, cobble, gravel, sands, and mud. Basically the size of the particle. We are currently working on a regression-based model, which basically guesses the size of the particle instead of aiming for a categorical variable. But as far as the categorical variable goes, we get some fairly interesting results. So you have here Pointe aux Anglais, which has very characteristic rocky formations here. This is going to get a little bit more obvious as we move along. We have very dense sediment rocks around. We have boulders on the sides here, which are there because of the cliffs. A little bit of gravel pits in the middle here. We have a 3D view available here that can be of interest. Basically, it just gives a little bit of a bit more of an idea how the different classifications map to the different 3D views. So we can see here that here each category is mapped onto a grayscale value, so that we actually can see well that the different category really reflect the different categorizations and different geometric characteristics of the environment. Moving along, we also have Franklin, which is one of my favorite areas here, namely because we have big underwater landslides here. You can actually see very well the different kinds of soils, and so you have your typical sand bottom, but where the landslides, you have larger substrates like cobble and gravel that are, in the landslide itself. You have larger boulders that are at the end here. You have a very large gravel field here, and of course, since the cliff is on the north side here, but you have your big boulders and bedrock here that are made very apparent when we actually watch the 3D view for it. But by watching the 3D view, we can actually see how the different substrates are distributed across the different landslides here. So you have a ridge at the top, and you have your larger substrates, which are basically slid at the bottom here. So we can see them a little bit better on this one here, but we can see the different sized rocks that have fallen down the landslides. So this is all grabbed through multi-beam echosounder, and hopefully it's derived from a very low density DTM. So the idea here is that we do not need a high resolution, let's say even LiDAR, like 3D LiDAR accuracy scan to actually derive the different kinds of substrates. We can actually grab that from the geomorphological substrates signature. So we also have GoodBoo, which is one of another interesting data sets. That's because this one, not because it's pretty, but because it shows the limits of the technology. Basically, we see here you have a very large rock formation in the middle. But if you observe carefully, you have a lot of lines here. So you can actually see that there's aberrations in the surface, and this is really to showcase one of the big problems with AI is that it's a garbage in, garbage out kind of situation. If you have errors in your DTM, it's going to give you errors in your classifications. So you can see that there are very weird and geometric lines here, and these are actually the overlap sections in between the two swaths, who create what appears to be a ridge where there isn't a ridge. So basically this appears like cobble, some sort of because there's some sort of an edge effect in between the overlap between the two sections. So as you see, of course, there are gaps in the DTM here. So the algorithm just basically tosses them away because there's no way to compute the geomorphological features on the entire neighborhood, because basically you're lacking a part of the neighborhood. So and we can see here, of course, the formation here. You will see them right there, that there is all sorts of different artifacts that are created. You can actually see that the boat was following the isobath. So you can see the noise here. Of course, you can see the boulders there that correspond to a different categorization. and of course a large sandy field, which of course also contains several rocks in there, but they're sparsely located. So the key idea here is that the different machine learning algorithms perform differently in different situations. So the idea here is not to rely as machine learning as a push button, but to be considered of the fact that it requires careful landmarking to achieve the best performance. Second of all, machine learning and AI methods are really vulnerable to noisy data. It's a garbage in, garbage out situation, so you really have to make sure that your data is flawless if you want a flawless categorization. And under these hypotheses, it does give you a very good, very accurate data. Of course, proper categorization matters because here we have a categorization derived directly from DFO's database, but DFO's purpose and our purpose or anybody else's purpose may vary, so the habitat models may vary as well. And for that, different feature sets will give different results. Finally, one of the interesting conclusions of this survey is that geomorphological models generalize fairly well across similar ecosystems. We've taken data from locations which are separated by several hundred miles, and hopefully we still get accurate data. So of course, the argument can be made that they're both from the St. Lawrence River, and in terms of ecosystemic, or let's say, similarity, they are fairly similar, and that would stand true. But the fact of the matter is that we can still get very interesting results by taking samples from an area and training the model and using that model into a different area. So in conclusion, while over 90% of the ocean floor has not been properly mapped, we are closer than ever. And hopefully machine learning and AI can help us fill in the gaps in our understanding of the oceans and hopefully bring us towards a better understanding of how we relate to the environment. So we'll be taking questions. If anybody has any questions, drop it in the chat, and it's going to be a pleasure to answer.